As you all know, the title of the talk today is Big Brains and Small Teeth, the Evolution of
I'm
Humans.
almost finished, so.
Dr. Monge currently is Associate Professor of Anthropology and keeper of skeletal collections at the University Museum. Working with Ellen Mann, Janet developed the traveling exhibition of human evolution entitled Surviving the Body of Evidence, the largest exhibition grant ever awarded to the University of Pennsylvania Museum of Archaeology and Anthropology, a 3-year, $1.7 million continuing grant from the National Science Foundation. Well, we're extremely happy to have you again.
Thank you.
And please go ahead and tell us more about this wonderful
Thank you.
findings.
First of all, I want to make an announcement in case you haven't heard, or any of you following what's happening with the Silk Road exhibit down at the museum.
Yeah.
Well, we've had a development. We are going to open it with artifacts and with
Oh,
mummies on
good.
the 13th. No, not on the 13th. I think it's the 15th.
The real.
The real stuff.
February.
So they did February. So they were able to make an arrangement with the Chinese. So unlike, what you've heard in the last couple of weeks, where they were showing just basically paper renditions of all of the objects and the mummies will be there. Thank you.
But only for a limited time.
Yeah, it's for a limited time, Aaron, and the thing is, I think that it's gonna, the mummies are gonna leave on March the 15th, something like that. So just if you want to have if you have an opportunity to get down there, I think it would be really worthwhile to see that exhibit. It's beautiful, actually, in its, design. So seeing it with the real objects, I think will be a real pleasure for you all. That exhibit that we just, we're hearing about, Surviving the Body of Evidence, that exhibit's been traveling around the United States, and so it's coming back to the Penn Museum. So for those of you interested in evolution and evolutionary processes, we're going to reinstall that at the museum too. So that'll be probably towards the end of this year or so. So there's some really great developments going on down there. I did give a talk on September the 20th, 2010, and in a funny kind of a way, I actually never got to any of the slides. How's that possible? And I actually got stuck on slide 1 and we never proceeded to slide 2. So we thought we would give it a second try. So this is Janet Monge. I should have put it on there. Janet Monge Redux. Okay, so this is the second attempt to get through the story of human evolution. And hopefully I'll be able to do a better job this time through, but I enjoyed the questions last time, and I think that's really kind of what held me from moving through the process, but it really wasn't being held. It was quite a wonderful conversation that I think I had with you all. So yeah, what I'm going to do today, if it's okay, and if we get through it, I want a really kind of course, it's sort of a short course in human evolution, talking about the connectivity of various things that we do see happening over the course of human evolution, and also to ask you to pipe up at any time if there's some insights that you would like to bring forward to the table. I would certainly love to hear. Human evolution has been a very contentious field. It's been that way for a long time. For whatever reason, people who work in this field can never agree on anything, and we do it in a volatile and nasty way. The only good thing about dealing and being in human evolutionary studies is when we get everything completely wrong, nobody dies. They're already dead, so that's a plus. We don't have to worry too much on that score. Anyway, I actually started out with this slide because I actually think that I'm the hair duplicate of this person. I have that crazy sort of hair going on, so this is my genetic ancestor. The story of human evolution is bumped out in sort of its kind of major frames. Many of the details, of course, are still kind of up there and open to different kinds of interpretations. We also have a great field in the sense that and it's time intensive, but we have got a great field in the sense that we have many people who are in the field collecting new fossils, so it's always in this constant state of flux and change. Okay? We also have recently layered in a lot of information coming from genes and genetics. Okay? One of the sort of the outgrowths of the genomics project has been, of course, the information that it's yielded for us in population histories, which has been super useful. Okay? So I know that in biomedicine, and certainly in the pharmaceutical parts of applications of biomedicine, it hasn't been as easily yielding information. But in terms of population history, it really has given us, I think, some really deep insights and new questions for us to think about. Very recently, they did sequence the Neanderthal genome, I guess the parts that were they were capable of extracting, and it's given us even more insights, including the fact that we can now deal with something that I think is pretty cool, okay? And that is that Neanderthals seem to be, I don't know how to say this so everybody would agree, but it seems to be that Neanderthals were contributors, okay, to modern humans in a genetic sense, okay? That they have contributed a fairly substantial portion of their DNA to modern humans. You'll sometimes see in the press that it's a small portion, but it's a 4% contribution that's lasted over the course of what amounts to at least 100,000 years, and that is indeed a significant contribution. As many people would say, and it's certainly true, okay, you only share about 8% of your DNA with your great-grandparents. So, you know what I mean to say that those lineages of genes have really kind of, really moved and not themselves become extinct over the course of that many generations is a pretty remarkable thing. So I, for one, am very proud to stand in front of you as a person of European ancestry and say I probably am a Neanderthal. I always knew that I had some deficiencies. Now they're just growing as I stand in front of you. We'll see how it turns out in the end. So we do have this. We do have this lineage. Okay? I'm also intrigued, and probably some of you are too. I know at least a couple people are, by the notion that these people occupied a planet that would have in this way been one that I can't even sort of conceive of, okay? And that is that at the same time there were two very different forms. Sometimes people say different species. I don't think that that's necessarily true, but two very different forms, human-like forms, humans and human-like forms, existing in the same environments at the same time. And I'm especially intrigued by that idea, I think. I wonder what we as modern humans would do if we were able to, see like a collateral species, basically just existing environments with us, and how we would actually probably initiate a lot of prejudices against them. That pretty much is what would happen. And annihilate them. Maybe that is in the nature of humans. Okay, I shouldn't say that, but I really don't like humans very much. I do like animals a lot better. So that are non-human animals a lot better. So that's the kind of lead off. So you have a sense of our sort of field. Okay. So now what's the kind of outline? Okay. And let's see if I can make it through these 47 slides or so. I'm going to talk really fast, I guess. Okay. I'm not positive how fast I can talk, but okay. We actually have lots of kind of cool information about our own lineage. We know that the origin of humans is in Africa. The earliest sites are found in Africa. And actually, in fact, there is no evidence outside of Africa of any one of these really ancient members of the human lineage. So one of the first things that I say, and I think is very powerful for a lot of students, is that we don't have to make up the fact that we're all African. We're really all African, and we're little variations of that. And I think that that speaks powerfully to groups of people out there in our classrooms on all kinds of levels. The first 2/3 of human evolutionary history were spent exclusively in Africa. So if you're thinking about humans as a species and, basically kind of our, our biological makeup as this independent species form, that is really nicely situated in Africa, and everything else is just a little kind of a variation on that, a little kind of jogging on that. Really, in fact, everything is best explained in that context. And it's mostly kind of Eastern and Sub-Saharan Africa, although there are inklings that we may be able to start to find fossils in areas like the northern part of Africa. And so, of course, many people have turned their attention to that area. We also, too, like Africa, as Darwin did 150 years ago, okay, and that our closest living relatives are also native to the continent of Africa. So, of course, it is those close relatives that are often used to model much about the early phases of human evolution, and for that I'd like to make a qualifying statement, and that is Chimps are always used, okay, as a model, okay, of early parts of the human lineage. A bit bothersome to me. Jackie is also a physical anthropologist, so she knows a lot about human evolution too. It bothers me a lot because, okay, the assumption is made that that last common ancestor was very chimp-like, and that humans diverged less from that last common ancestor than did humans. But indeed, a lot of new fossil evidence seems to indicate that even at the inception of our lineage, okay, we have, sort of layered in or puzzled in a whole host of very unique features that are very unlike anything that we see in a chimpanzee. Okay. So chimps, and this has of course led to the confusion that chimps are, and my students say this to me all the time, chimps are our ancestors. And I'm like, well, why are they hanging around here? Okay. I mean, chimps are not our ancestors. Okay. They're a relative, okay, basically, and we do have a common ancestor in the not too distant past. It's something like about 7 to 10 million years ago. Okay. Anyway, we don't have any fossils in the early phases of human evolution, which are contained in the sediments of a likely time period in Europe or in Asia. With all of the sort of rhetoric about humans and what a human is, I'm sorry the print is so small on here, but the details are not so meaningful, okay? But the point of the slide is, okay, that we do have this last common ancestor that has, essentially many things of commonalities between living humans, chimps, but going back in time. And our first sort of layered in group of anatomical features that really kind of makes us a unique lineage is a not very spectacular thing, and that is that we are two-legged walkers with trunk balance that use our legs in a stride or a striding gait. And that is, not the way we like to think about ourselves as these brainy, culture-bearing critters and all that sort of thing. But that's a very, very late development in human evolution. At its inception, okay, we basically start to see movements away from quadrupedalism into a two-legged walking pattern, and that really sets the stage for everything that happens in human evolution from that point onward. Associated with changes probably in diet, environments, and of course the evolution of the brain, which is probably one of the sort of most key group of changes that has indeed occurred in our lineage. What are the unique attributes of living humans and when do they occur in our lineage? Always one of the sort of great topical areas, and the ones that I think are most riveting to our students are these. And a lot of these are indeed pretty intriguing and probably related to each other. But the problem for us is that the fossil record doesn't give us such a great insight into some of these. So of course that's, I think, why human evolutionary studies are so contentious. They're contentious because we can't really find the evidence of this. There is no finding of this evidence. This is the untangibleness, essentially, of dealing with a fossil record. And there's some great things in here. Some people put aside some parts of them or don't think about them, but they're really necessary components of humanness. Like for example, all of the features that are associated with reproduction. Assisted birth. That is probably something, a necessary component to birthing in humans, because of course we have so many complicated processes that are associated with birth. We have unique phases in humans that are associated with middle childhood. When did these kinds of things layer in, and how do we understand them as part of parcel of this whole process? We can't really answer. For me and Alan Mann, my colleague, we think that this may be an early kind of development, and of course that's the key piece that allows us to see all of these other kinds of, especially behavioral changes.
How far back do we go to assume that there was assisted birth?
Yeah. Yeah. Fast answer or a long answer? If I give the long answer, we'll never get to slide 5. I'm going to sit down and answer. All right. When do we think that happened? We think basically it happened at the junction in which members of our lineage, probably the earliest members of the genus Homo, who had over time experienced vast, okay, increases in brain size, okay, would have hit a limited point, okay, in the structure of the pelvis in which they could produce, okay, infants that had a brain size, okay, which was in proportion to adult brain size and adequately to have been pushed through this birth canal, okay. The restrictions of our birth canal are associated with bipedalism. That's kind of a given. There's not a lot we can do about that. But it comes layered into that very strong selective pressures for increases in brain size. And this would have created a kind of a conflict between brain size and brains of babies, because they've got to go through this canal, brains of babies and the selection pressure, okay? So maybe 2 million years ago or so, okay, it might be about in there, okay? And at that point, we have a doubling of brain size in the human lineage, so our early little bipedal critters, probably no problem. And then you have all other kinds of adjustments, okay? So we produce these babies that aren't exactly like, you know, the kinds of infants that we describe as altricial and all these other kinds of things in other mammals, okay? We actually sometimes refer to human babies who aren't really particularly altricial. We refer to them as extrauteral fetuses. And pretty much, okay, yeah, they're these blobs. Now, I don't have any kids, but when I do see them, I'm always kind of amazed at how blob-like they are indeed. Okay?
So there is a big hiatus between the assumption that you say, you know, the largest, the birth canal and all that, and then the first written evidence that there were such individuals that assisted.
Written evidence?
Yes.
Okay.
When is it?
Oh, a huge
3,000?
gap
Yeah.
between these, you know, between this part of human evolutionary history and really the beginnings of history, written history. Okay? So we assume that there is assisted birth, okay, because we think that females with this constricted birth canal, basically the way humans, moms, basically eject the babies, okay, is that the baby, and it sounds crazy, okay, but the baby actually, it's like they're being screwed out of the birth canal. I mean, it's literally like that, okay. They twist through the birth canal, okay. And because of that twisting, okay, their presentation oftentimes is with their faces downward or away from the mom's belly, okay. And so that, of course, would have created a lot of, you know, interesting possible outcomes, okay, especially if there wasn't, you know, some birthing device, okay, or some kind of birth assistance that was just beyond what a mom could actually accomplish during this process, okay. All right, anyway, what do we know about human evolution? I mean, now that I told you what we don't know about human evolution, what do we know about human evolution? We have the basic framework of human evolution. We basically know many of the things that occurred over the last 6 or 7 million years ago or so, okay? And, you know, we can kind of bump that out in its sort of sketchy details. I mean, the really cool parts to it are a little bit more elusive, okay? But, you know, we do know bipedalism starts it off, okay? They start out with these great big faces and massive dentitions, and we wonder what the heck they were doing with those massive dentitions and teeth, but it's chewing whatever they want. I guess that's the assumption. Okay. Then you start to layer in increases in brain size, and then you get much reduction in the overall dimensionality of the face. Okay. And then, of course, about 100 to 50,000 years ago or so, we begin to see modern humans, what are called modern humans. Okay. And okay, nobody, okay, has ever been able to effectively define what a modern human is. Okay? Isn't that interesting? Okay. So one time, two human evolution people, well, I'm sorry, just really one human evolution person, wrote a paper in the Journal of Human Evolution, which is one of these well-cited ones, at least in the field of biological, physical anthropology, and human evolution. He writes a paper in which he's actually going to define modern humans, okay, and he wound up, okay, actually defining modern humans, okay, that excluded a whole mess of modern humans, okay, and not just like the odd modern human with the peanut brain out there or something like that, but it was like whole populations of humans were excluded, okay. I mean, like, that's a different story. I mean, the odd human here or there is really okay. You know, how you put all that variation together into one little pot. And no one's attempted to do that since, and I think that makes sense. I mean, why would you do it? It's going to be a fool's game to be able to do it apparently. We do have a lot of variation, and it's hard to, put it down into, a couple of phrases or one 25-page paper or something like that. Okay. We do know that at certain points in human evolution, we have lots, okay, of lineages. Towards the end, probably 2, maybe 3, depending on the people that you talk to. Okay. But at other points of time in the past, we are looking at a very different world constructed around a whole variation in these things that are very similar to ourselves. Okay. And they, at the time, were very similar to each other. So of course that brings us to, trying to understand and speculate how they were interacting with each other. Okay. And we don't really have a sense of it. They might have been eating each other for all we know, which would be kind of fun to think about. Okay. Very nice view of it, I think, here. So you can see those skulls. Okay. We don't have enough fossil record in human evolution to test most, okay, of the mechanisms responsible for evolutionary change, like so some of you will kind of take a neo-Darwinian perspective or a punctuated equilibrium perspective. Is it fast? Is it slow? Is everything adapted? All those kinds of questions I don't think we can address very effectively with the fossil record. I talk about a lot of fossils, okay, but basically we have the whole world, okay, spread with these fossils. They range over 6 or 7 million years, okay? And there is maybe, I don't know, I'm always kind of making these numbers up, okay? There's always, maybe 10,000 fossils representing all of that time, okay? So we don't have kind of a fine layering device to really kind of see exactly what's happening at various junctions, which is kind of bad, okay? It's good in the sense that we can speculate, kind of in a fun way about it, but we can't really, in a sense, evaluate, okay, some of the sort of the bigger ticket items, okay, that really have to be addressed with a fuller and a deeper and a larger kind of a fossil record, okay. Basically, read your shellfish of various sorts of things like that, where they can have millions, okay, in their samples, okay. We don't have that, okay. And here you go, just as a kind of a sort of a better version of the same scheme. Okay, we do have in human evolution recently a lot of noteworthy finds, okay, including an entire issue of the journal Science devoted to the analysis, okay, of these fossils which are placed in Ardipithecus ramidus, and some of you might have seen that several months ago. Okay, now, okay. The excavators of those fossils, okay, actually brought the fossils out 15 years ago. We also have one of the world's slowest fields, okay? So they found the fossils 15 years ago, and they actually then described the fossil 15 years later, okay? And an entire issue of Science, and covers, obviously, the cover story and everything else that goes with it, okay? And that was the big one, okay, Ardipithecus ramidus, okay? Why does it take so long to do this? Good question. They do reconstructions. They bring in other experts. They don't show people their fossils. We have that problem in our field, that nobody shares data. I'm sure it's true of other fields too, but we're really bad in human evolutionary studies. I don't know if it's hit as badly, well, I keep saying nobody dies, basically, if they don't see our fossils. But, not sharing data, I think, is a really big issue in human evolution. And so this big journal comes out with all of these descriptions, and everybody's arguing about this or that thing. Okay, we're about probably to get more fossils that go deeper, okay, into this range closer to 7 million years described in the next couple of years too. So it'll be interesting to see what happens. Okay. Yep, the first thing, okay, that we really can talk about is bipedal or two-legged locomotion. A freaky kind of a locomotion system. It's not like the bipedal locomotion of any other animals out there on the planet. I mean, when we talk about bipedal locomotion, I've already said it, it's with trunk balance and alternative leg progression. Okay, you have hopping animals, you have animals that use tails for support and all kinds of things. Okay, but the stride, okay, with the trunk completely balanced over the pelvis, okay, is indeed pretty unique. There's arguments about how efficient their locomotor systems were, or whether or not they really exclusively used bipedal locomotion, okay? And then the question, of course, becomes if it's the key or the crux feature, you know, essentially how do we understand its origin and how is it linked to all of these changes that do occur later on in the lineage, okay? I think that it's probably pretty clear, okay, that without bipedalism, we would not see a lot of the kind of lockstep changes that we do see in human evolution. It's not very likely, okay? Including, you know, things like increases in brain size. And yes, okay, we do have this freedom of the hands, you know, from the activities associated with locomotion, okay? But that seems to be an outcome of bipedal locomotion. It's not, you know, it's not something that's associated with the beginnings of locomotion, although Darwin did link those two things together. And then you can see a lot of the anatomical differences between our close relatives and ourselves, okay, and locomotory systems. You know, the skeleton is really easy to see bipedalism, okay? It's odd, you know what I mean? There's this balance stuff going on. We asked before about the pelvis and what the birth canal looks like. Okay, so here is one of these early bipeds. Okay, here is actually this is a Neanderthal pelvis, and this is a modern human pelvis. Okay, looking at into the birth canal. Okay, so this one has a brain size of about 400 milliliters. This one has a brain size. It kind of looks a little kind of funky here, but has a brain size of about 1,500 milliliters, okay? And this one has an average brain size at about 1,300 milliliters. If you read the literature on human evolution, the statement is made because, you know, we're the great accumulators of measurements, okay? So we're talking about things dolicho and brachycephalic and all this kind of crazy stuff. You'll read in the literature that the average brain size of a modern human is 1,450 milliliters, okay? I have no idea where that comes from. We measured our entire collection down at the Penn Museum, and our average brain size is about 1,200 milliliters, okay, in terms of volume. Yeah. Where did the 1,450 come from? I'm kind of not kidding. Okay? It's one of those things we try to track back and figure out. Okay? The range of brain size actually in our collection, so we're obviously not sampling everything possible out there in the world, but let's say in our samples we've got great collections at the Penn Museum of about 10,000 skulls. Okay? Our smallest, okay, is a brain, or head, okay, belonging to a woman who's described as, I kid you not, the little lady from Tübingen. And the little lady from Tübingen, okay, has a brain size of about 600 milliliters, okay? Yeah, and then we have the man who was called, okay, they all have names, and they know who they were in life, which makes it a little amusing, okay? So the little lady of Tübingen on one side, and then on the other side we have the Dutchman, okay? And the Dutchman is 2,100 milliliters, okay? So yeah, it spans kind of maybe they took those two and made an average. I'm not really sure yet.
Are you sure those are female pelvises?
No. In fact, we know this one in the middle is not a female, okay? So we're always trying to push babies through male pelvises in human evolution.
Because this male and female
I
pelvis
know.
are clearly different.
Absolutely, okay. Well, we're still using the males, okay?
Maybe they were hermaphrodites.
It could, real possible. And this, of course, has been a huge critique. The only pelvises we have of Neanderthals, for example, are males. Yeah, there's only one female, and that is this, and it's even contentious as to whether or not it's a Neanderthal from the site of Kabul in Israel, okay? And for some reason, that's a teeny weeny little person as well. But you're absolutely right. How are you reconstructing a birth canal, okay, from a male pelvis, okay? I mean, it would be like trying to shove a human baby through a male pelvis sitting in the room, okay? You know what I mean? It's just not going to happen, okay? Yeah. Yeah. This game, I mean, basically, I mean, am I mistaken or what? Sounds like you know your pelvis, okay? So this is a male pelvis, okay? This is not a female pelvis. And this is the slide that I took actually from an illustration on human birth, okay? Very narrow, okay? It's a little wide in the subpubic angle, but I mean, in terms of the, you know, usually in females you have a greater flare on the ilia and all other kinds of things, okay? This one they call a female, it's Lucy. You might have heard of Lucy, the famous fossil Lucy. Well, get this, about half of the people think the famous fossil Lucy is actually a male. Okay. Yeah, I know, like, holy smoke, so we're constructing everything based on the wrong models, okay? This, by the way, is from an Israeli site, Kabara, okay? I should have brought some bones in, actually, shouldn't I? Next time, if you invite me back, I'll bring some bones in. Or maybe you can meet down at the museum, although they say it's too far at the end of campus for people that want to do the trek on down. Yeah, but I would love it if you could, truly. We have all of these things and casts of all of these things also, too. We can walk, I mean, absolutely, and have a nice walk. We'll have to do it in the spring, because today was sort of miserable walking here. And here's the reconstruction of the infant going through the birth canal thing. And this is Lucy in the center. Okay? And here's a modern human in that twist that we talked about moving through the birth canal. Okay? And okay, the blackened areas that you see on the side, okay, represent basically space, okay, within the birth canal. So you can see that humans really are not very well spaced in the birth canal. There's little sort of room for them to maneuver and going through the birth canal. Chimps, I mean, basically they kind of go off and, you know, mom's about to give birth, gives birth, picks up the baby, comes back, and, you know, is foraging for food. I mean, I know some human females can do that too. It's not that every woman has difficulty in the birthing process. It's just that a significant portion of women do have problems in the birthing process. Yeah. So that particular setup, okay, is indeed associated with increases in brain size and a pelvis, which is very restricted based on bipedal locomotion. We'll take a look at some of the skeletons. Okay, so this is this 4 million year old Ardipithecus from science. This is Lucy, okay, and this, okay, and I put it in there for the drama of it, okay, is this early member of the genus Homo that comes from Lake Turkana, okay, because another, okay, kind of layer of discussion in human evolution is body size. Okay. So what's happening there, okay? So really, indeed, okay, between the 3 million years, okay, and 2 million years, okay, the differences in body size are really dramatic, okay? And again, that's another kind of point of contentiousness, okay? How do we understand that?
Well, isn't the, what was it, Nakario?
Narukatomi boy?
Yeah, Narukatomi boy.
Mhm.
He was assumed to be rather tall, on the tall end of the species, and also had scoliosis.
Here's a neural tube defect, okay, that they never talk about in the literature. He has some kind of a neural tube. He has really, really small vertebral canals,
Yeah.
and he's got open, okay, non-fused, okay, spinous processes in the back, okay. I mean, which, for all accounts, I mean, I think if we saw that anywhere except in the fossil record, we would make an assumption that there's some kind of a pathology associated with it. But nobody talks about it being pathological. I mean, I've heard papers, Jackie, have you heard papers? Have you heard papers on it being described as pathological? But I've never seen it in published form. It might be one of those kind of things that people don't want to describe as a pathology.
Oh, this was a personal communication.
It's a personal, very personal communication. Damn it, that thing's pathological. Why are they describing it this way? It's also a kid. It has open growth plates, okay? Yeah. So it's like this gigantic kid. It's like a gigantic 9-year-old thing. What's going on with that? And like, so we start to see like Kareem Abdul-Jabbar in the fossil record. Something's up, okay? You know what I mean? Like all of a sudden, coming out of the peanut moms and Kareem Abdul-Jabbar, okay? Dr. Ruth, okay, and Kareem Abdul-Jabbar, okay? You know, how does that happen? I don't know. Okay? I think this is a pathology. I personally think it makes the most sense, but it's not described that way. So we try to understand those increases in body size also too. Again, and how does that influence brain size changes in human evolution? Because of course there is a correspondence between those things, and so how do you factor that in? And then you could say to me, Janet, maybe this is just, you know, this one sort of freaky skeleton. What about all those other early members of the genus Homo out there? And lo and behold, we don't have any other members of the genus Homo who we can estimate body height on. Okay, we have a couple of isolated bones here and there and stuff like that. So it hasn't been easy to even think about body size increases. Okay,
How
a
good is
simple
the
thing.
age determination?
How
And
good
how
is it?
old are these people?
Like at death or age in terms of?
Yeah, at death, how old were they?
Lucy is an adult, okay? So, they was actually kind of say a young adult. So whatever happens at the eruption of the third molar, whatever age that is in her species, okay? So, it probably isn't 18 to 20 or something like that as it would be in modern humans, okay? But she certainly is at her maximum growth, okay?
In all of these very early fossils, is there any evidence of bone metastases in any of them, which would be quite distinctive?
And I've looked this up carefully because we think we have the first example of a cancerous tumor in the fossil coming from the site of Krappen. It's 100,000 years old, okay? And that we just picked up on we did a radiographic atlas and a CT atlas of the materials. It's a huge Neanderthal site with there's 900 bones from the site. And that a retired radiologist from here from Pup, Maury Cricken, actually is the person who was looking at it and said that it is some kind of a growth. And that might be the earliest evidence we have of any growth like that, okay, in any fossil in the whole of human evolution. Okay. Yeah.
For tuberculosis?
Like bone tuberculosis, as far as I know, no, okay.
Syphilis?
Syphilis, no. With a lot of bone disorders, okay, it's just hard without having other structures to be able to isolate it to particular pathogens. We have some sick-looking skeletons sometimes, you know what I mean? But it's hard to kind of say from whence it comes. Most infectious diseases probably wouldn't have been that rampant in the time because there's very little population density, so you wouldn't expect, this is the thing that said, you wouldn't expect a pool of people that would be able to succumb to new infections, and you would have this infectious process of, basically people transmitting things to people on a regular basis. Where the density of humans is maybe 6 per, kilometer, something like that, yeah. So we don't really see too much of that. And we don't see too many pathologies like this. And chances are really high that most pathologies would have been very sustainable, okay, given the fact that they're all responsible for extracting resources from their environments. Yeah.
The very tall individual
Yeah.
could be a result of physiological development, but could also be a tumor in the hypophysis,
Yeah.
producing
Yeah.
a large amount of
Yeah.
growth hormone.
And we've said,
that's why maybe he died early.
Listen, we've said many times, wouldn't this be great, okay, to see an X-ray or a CT scan, because you could see the cella turcica? You know what I mean? We have mummies, for example, that, we can see an enlarged cella turcica, and have come to the conclusion that there was some pituitary phase disease, okay? On this, I've never seen a CT scan done of the specimen, okay? I think Kenya, okay, a lot of times when you see fossils in a lot of the developing countries, they obviously they have the diagnostic tools there that are situated in, pretty well instrumentized hospitals, okay? But in terms of their availability, the CT scan a fossil, if I'm like 20 people are dying outside the hospital, we're not going to CT scan a fossil, really. It doesn't make a lot of sense, okay? So you don't see a lot of analysis like that in a lot of the developing countries, not just in Kenya, but in other places too. We were able to do all of this in Croatia because, of course, it's a European country, you know what I mean? They have, nice hospitals, they have portable CT scan units and portable radiographic units and all kinds of stuff. You asked me better questions in my talk, so keep talking. And, here you go, like, there's the fossil record of one species in human evolution. I love this one, okay? And this was in 1979, and that's everything, okay? That is Lucy, okay, and everything that's placed in the same species with Lucy, okay? Everything at the back of the table, okay, are chimpanzee heads from the collection of the museum that this was photographed in, okay? So this is the whole, like, this is our fossil record, okay? It's crap.
If these guys
You
could
know
talk,
what I mean?
this could be a Tower of Babel.
Yeah. I mean, like, look at that. I mean, that is not what you would call easy to look at or interpret. Okay? It's a mess, it's poultry. And so, okay, in a lot of the early, studies now, okay, the chimpanzee, okay, it used to be used oftentimes as a model for early phases of human evolution, appears to be sort of fading away from that particular place. Okay. Of course, they did this developmentally all of the time. They still use a lot of primate studies in human evolution. Okay, a little bit in I should say many interesting ways. Okay. They do all kinds of physiological studies with chimpanzees as a proxy to humans. Okay, all kinds of growth and development studies too. Okay, and they're all used to model essentially the early phases of human evolution. Okay, what time do you all have? Okay. What time am I supposed to shut up?
I don't know.
When you get tired.
When I get tired, okay. When everybody falls asleep. Poke me if I start to fall asleep, okay. What happens in terms of the dentition? Also some interesting questions. I actually kind of like the dentition probably more than anything else can. That basically, as a modern human, okay, this is a comparison with an orangutan, we've got all of these forms, okay, that have very large faces and musculature, okay, which operates the teeth, okay, and our challenge becomes, what the heck are these critters eating, okay? So if you have an interest in diet, okay, it's also an interesting story to tell in terms of human evolution. And you know what everybody always says to me, okay, probably Jackie too, okay, what everybody says to me is this, okay, I read that the evidence seems to suggest, okay, that humans are supposed to be vegetarians, okay, that, that's our original dietary niche, okay, that they've got these big teeth and big muscles that are associated with chewing vegetable matter, and that, whatever they were exploiting, it primarily was in that kind of realm of food sources. Okay. And yes, for a long time, at least with some of them, we made an assumption that these were vegetarians of various sorts. Okay. And that, of course, eventually we came to look at this in a lot more detail and also, too, produce a lot more chemical analyses of these things. And guess what? Okay, it seems like they are just like us, okay, complete and total omnivores. Okay. In other words, one of the probably interesting things about humans is our lack of specialization. Okay, not just in the dentition, but probably in most things. Okay, that we're almost like, other animals, of course, have a lot of plasticity, and especially in behavior. Okay, humans seem to be like hyperplastic. Okay, in terms of behavioral repertoires, in terms of diet. Okay, so on the planet today, we have humans, okay, that seemingly can exist on a bowl of brown rice a day. Okay, and then humans, okay, who exist, and nutritionists would tell you they should be dead. Okay. Yeah, they would tell you that they should be dead, that exist exclusively on meat. Okay. Why are they not dead? Okay. Maybe it's not just culture that we internalize. Maybe it's all of the issues that are associated with what foods we can tolerate and what we can extract from those foods. So when the United States government gives guidelines for good nutrition or diet in humans, okay, they kind of mean like the average Joe out there, okay? And then, of course, most people are taking, sort of cues from those guidelines. They're probably really good, but indeed, okay, we probably are all not digestively the same, okay? And that indeed you can't probably, move into wholly different kinds of realms, okay, in terms of specializing and processing of various kinds of food sources, okay? So when everybody says, okay, we're vegetarians, we're this, we're that, I always say the following thing. If human evolution is going to tell you anything about food, it's going to tell you the following thing, okay? Don't eat the same thing every day. Okay, that's pretty much it. Okay, and anything that's food, eat it. Okay, that's pretty much what it says.
That's what we've been doing.
And also, to another thing is probably, okay, don't eat a lot of it. Actually, which I think intuitively we've come to that point. Okay, yeah. So eat anything, eat it diversely. Okay, maybe eat it seasonally. Okay, depends. Okay, but eat it seasonally and don't eat a lot of it. Okay. But probably one of the biggest things with humans that we kind of learn from this whole thing is get up and move around. And if we have a species characteristic, it's obviously based in a very active lifestyle, which is one of the things we have really completely removed ourselves from, and so it's probably a pretty key thing. I don't want to labor the teeth, although I love them, because it was 5 of one about a half an hour ago. So, oh God, I know you're probably more interested in other things. Okay. We've got really cool teeth, though, too. Okay, what's going on with that? Okay. Chimps and all of these other primate cousins of ours have big projecting canine teeth. They've got limited glideability of their lower jaw. Our lower jaw actually almost attaches and slides around. Okay, it's called rotary motion. Okay, it goes like this, it goes like this, it goes around like this. Okay, and all of that is because of our relatively flat teeth. Okay, and our real thick layers of enamel on the chewing surfaces of our teeth, so we can process lots of even coarse foods. That's why I say eat anything. It's probably a pretty good thing. Okay. We have super powerful jaw musculature, okay, as you know, witnessed by the obesity rate in the United States. Okay. And so, like, basically, you know, they really took to heart, you know, that they can chew anything and eat anything, okay, including apparently the dining room table. Okay. So we've got all of these mechanisms for really sustaining a pretty broad diet, and that's really, in all likelihood, what we should do. Okay. A lot of our ancestors had massive big teeth. Okay. Again, I don't want to labor a lot of the details on teeth, so we can just take a little peek at brain stuff before I have to wrap up. Okay. One of the big things that are reduced in human evolution are the sizes of the canine teeth. Okay. By the way, in primates, to go back when you were asking me a question about socialization and these kinds of things, the canine teeth in primates are used primarily for threat gestures. Okay? In humans, okay, we don't use that particular device in terms of threatening other members of our own species. Okay? Chimpanzees are even when they eat meat, they don't use canines like big canine forms like the cats do to deliver a killing blow, or to grab onto and gyrate like a dog does. Okay, its prey until it breaks its neck, okay, or kills it. Okay. So the function of canine teeth is really interesting in the history of our not only our lineage, but a little bit broader even back, you know, with our primate cousins out there. Okay. Why that tooth reduces in size has been interesting. Okay. We had a much speculation on this too, and my favorite speculation was in 1972. When a brain evolution guy, okay, said in the American Anthropologist that the reduction of the canine tooth, okay, was, and he was making a joke and people took him seriously, okay, that it got in the way of people kissing. Okay? Maybe it's that. I mean, like, at least that's a fun explanation of it, you know what I mean, versus the serious ones where we don't seem to get any closer to the mark. Okay? Some of those little teeny critters that we have back there have like really, really massive teeth. Okay? There are some, Lucy has a third molar tooth that is a third again larger than our own molar teeth, even though she's a third of our body size. Okay? So that's when they talk about big teeth. Sometimes they're called megadons. Okay? Microcephalic megadons. Okay? Teeny brains, big mouths and faces and teeth. Okay? Changes occur, of course, in the skull, okay, over human evolution, and that, of course, would be the last bunch of slides in here, and at the point at which I must end, because I think I have a 2 o'clock class, so I can't go till way past about 1:15, something like that. Okay. Our brain, of course, is our constant obsession, okay, in human evolution and understanding the developments which have occurred in the course of our lineage. Okay. It is probably the least well understood of any of the complexes, okay, in human evolution because, of course, the brain is a soft tissue, leaves no evidence. Okay. So we study it by the internal dimensions of the skull bones. Okay. And there is a whole field called paleoneurology, okay, which really tries to get at the maximum amount of information on this as possible. Okay. Certainly, okay, we can say a couple of things. Okay. One of them is that we have a brain size, and you can see here listed on the slide, it's a little bit too high, but we have a brain size which is significantly different from our closest relatives, the chimpanzee. But it's not actually the brain size which is really key. Okay? I mean, obviously there's brain size issues in this game, but the real key features are generally associated more with the organization, okay, of the tissues, okay, within the brain, okay, than just the size or the dimensionality of the brain, okay. And of course, many people do just concentrate on brain size, okay. So this is brain weight in milligrams and body volume in grams, and of course they give a very famous paleoneurologist by the name of Jerison gave a factor of sort of encephalization, sort of beyond the vegetative, called the encephalization quotient, and you can see where our ancestors kind of sit, and a lot of the apes sit, and of course we're always talking about humans as being a very highly encephalized species, and trying to understand, really why that happened. Why did we have such strong selective pressure for increases in brain size? And obviously it's associated in some way with increases in cultural complexity. This is one of these inside of skull bones of one of these early fossils, and people are feeling the bumps. Okay? You know, what do they tell you about the bumps? Okay? That's the kind of stuff that you have to deal with. Okay? So you can feel the bumps on these internal casts made of the skull bones, or you can look at the outcome of the brain in culture. Okay? Tools and how they modify the environment, and do they build structures and those kinds of things. Okay? And those are the tools, in a sense, okay, for understanding at least a little bit about the evolution of behavioral complexity. So here's one of these bumpy early, remember our lineage brains, here's a chimp brain. So chimp brains have, particular structures like the lunate sulcus, which is a demarcation sulcus between the parietal and the occipital lobe. Where is it positioned? Okay. Is it high as it is in chimpanzees, or is it low down as it is in humans? And what does that mean in terms of the differential expansion of particular lobes of the brain? Okay. Because of course we do have lobular organization, which is quite different than chimpanzees, and that's key. Body size and brain size, they obviously are being associated with each other, and people are attempting to understand. Okay. And the final group are sort of little bits in here, okay, has to do a bit with culture, okay, and understanding things, for example, like the origin of language, okay, and when did that layer in? Some people think, based on these brain size issues, okay, that, not brain size, but brain organization issues, okay, that you do have a kind of a disjoint, okay, in early in human evolution from what we would see in terms of the brain of it's not a bigger chimp brain, okay, it's a reorganized brain, okay. And a lot of people say that it's reorganized in the areas which are associated with language and cognition, actually, okay, it's possible, okay. And of course then, okay, when or how do we think about the origins of language, okay? And I would say that based on the quantity of pages devoted to this, that it is a highly contentious part of human evolution and not an easily resolved one. Okay. There are many people, okay, who at this junction actually think that Neanderthals, for example, okay, are language bearing. Okay. This has to do not only with the sort of the overall size of their brain, but the organization of their brain, okay, but also too, based on the cultural context of a lot of their sites, they have very complicated behaviors, hunting behaviors that are probably social behaviors and things like that. Neanderthals also too, okay, are the topic of a lot of areas of discussion and debate in human evolution, and this is a full-mounted Neanderthal skeleton and a full-mounted modern human skeleton. A lot has been made of the differences between the two. Okay. A lot of people say Neanderthals are the sort of the power packs, okay, and that modern humans with the sort of slight or more gracile skeletons, okay, substitute culture for brawn, and that's the difference between them. Okay. We do know from dentitions and things like this of Neanderthals, okay, that they were using their teeth as tools, okay, but also too, okay, we have lots of data from stone tools, okay, that are part of the human fossil record, okay, and that in itself, okay, becomes a data source, okay, in human evolutionary studies, okay. I don't want to necessarily, go through a little refresher on what the Paleolithic is and things like this, okay, but okay, basically, okay, over time, at least in Europe and in the Middle East, where we have some really excellent sequences, you see increases in the complexity of various kinds of tools and tool technology, which has been associated oftentimes with things beyond just the tools, but with symbolism and with language. Okay. We have experimental archaeologists who try to make stone tools and use them as our ancestors would have done. Okay. So here we have Nick Tock who butchered, I don't know, a cow or something like that. This would be like, I always say, like the day that somebody makes me make a tool and butcher a cow is the day I find a new field. Okay, that would not be my best day. Okay? Anyway, they, experiment to see how it's made and the complexity and what, what hand-eye coordination is necessary to do it. Now, of course, they can do these functional PET scans and get a sense of how the brain is used in making these tools. And, we have all these GWAL papers about these kinds of things. And, certainly the tools, when they begin, are relatively simple with just a couple of chips out of them. But by the end, they become quite elaborate and quite complex. Okay? And these, these are 1 million years old. Okay? And over time, okay, they become further refined. They become almost, at first they're very sort of globally distributed, and then they begin to be defined particular regions as like styles and things like that. So of course, your mind goes more to thinking about what something like that represents. And then of course, in the end, we have these, at 40 and 50,000 years ago, we've got very elaborate tools, okay, that, basically if you just look at you know that these are fishing items, like, like they look like fishing items you or I would make if we were whittling on our patio one day a piece of wood, okay. And this, of course, is a bone needle, okay. So yeah, there you go. Okay. So human evolution, okay. Basically, we kind of went through it in a quick and dirty way, okay. Then we got the power tool, and of course we got the real power tool. Mine's probably about ready to blow a fuse or to run out of battery power or something like that. So I'm going to shut up and ask you if you had a couple questions or anything like that. Okay, I gave you the quick and dirty of human evolution. What can I tell you?